Here is a question that trips up almost everyone. A test for a rare disease is 95% accurate. It comes back positive. How worried should you be? Most people answer 95%. The real answer is closer to 1 in 3. And that gap is the whole point of this lesson. The trouble is that the lab and the patient are asking two different questions. The lab measures one direction. The patient needs the other. The lab tells you the chance of a positive test, given that you truly have the disease. That's what sensitivity measures. Effect, given cause. But you care about the chance you actually have the disease, given that positive result. Cause, given effect. The arrow points the other way, and the two numbers are not the same. To flip the arrow, we lean on one fact you already know, the multiplication rule. The chance that two events both happen can be written two ways. One way, start from the cause. The chance of the cause, H, times the chance of the effect, E once H, is known. The other way, start from the effect. The chance of E times the chance of the cause, H once E, is known. Same joint probability, two honest roots to the same corner. And if both equal the same thing, they must equal each other. The seed of everything that follows. Set the two expressions equal. The blue side, from the cause. The gold side, from the effect. We want the cause given the effect. The gold conditional. So flip the equation around to put that term on the left. Now divide both sides by the chance of the evidence, P of E. The evidence cancels on the left, and what remains is Bayes' theorem. There it is. The probability of the cause given the effect equals the probability of the effect given the cause times the prior over the overall chance of the effect. One quiet condition rides along. The chance of the evidence must be greater than 0 because we're dividing by it. Every piece of this formula has a name, and the names tell a story about updating a belief. On the left, P of H given E, the posterior. Your updated belief in the cause after seeing the evidence. P of H is the prior. What you believed before any evidence. How common the disease is to begin with. P of E given H is the likelihood. How well the cause predicts the evidence. How loudly a true case sets off the test. Strip away the symbols, and the rule reads like plain English. Posterior equals likelihood times prior over evidence. It's a machine for updating belief. Start with a prior. Let evidence arrive. And Bayes hands back the posterior. Your old belief, revised by what you just learned. Let's make it concrete. Three numbers set the scene. First, the prior. 1% of people actually have this disease. Second, the sensitivity. If you genuinely have the disease, the test catches it 95% of the time. And third, the false positive rate. Even a healthy person tests positive 2% of the time. Small, but it matters enormously. You test positive. The question is the posterior, the chance you truly have the disease. Before any algebra, let's just count people. Percentages hide what's really going on. Picture 1,000 people, 1,000 dots. Let's split them by who is actually sick. Remembering the disease is rare. Out of 1,000, only 10 truly have the disease. The 10 in violet. The other 990 are healthy. That imbalance is the heart of the story. Now run the test on everyone. Among the 10 sick people, the test is strong. So essentially, all 10 light up positive. In green, 10 true positives, but now the healthy. 2% of 990 is about 20 people, and the test flags every one of them anyway. In rows, roughly 20 false positives. Here's the punchline, and it's worth pausing on. Line up. Everyone who tested positive. About 30 people in total lit up. 10 of them truly sick. 20 of them perfectly healthy. So of every 30 positive tests, only 10 mark a real case. 1 in 3. That's why a scary positive, on a rare disease still leaves you more likely healthy than sick. That counting story is exactly what a probability tree draws. The first branch asks, are you sick? Up, 0.01, disease. Down, 0.99, healthy. The prior, drawn as a fork. From each branch, the test splits again. If you're sick, positive with probability 0.95, the sensitivity. If you're healthy, positive with probability 0.02, the false positive rate. Multiply along each path to reach the tip. Sick and positive is 0.0095. Healthy and positive is 0.0198, nearly twice as big because the healthy crowd is so much larger. Now the algebra just retraces the tree. The posterior is the likelihood times the prior over the total chance of a positive test. The one thing we still need is that denominator, the overall chance of testing positive. By total probability, it's the two positive paths from the tree, added together. Plug the numbers in. The sick path gives 0.0095. The healthy path 0.0198. Add them, and the chance of any positive test is 0.0293. Everything is in hand. The numerator is the second positive path. The denominator is that total 0.0293. Divide, and out comes about 32%. Not 95. Almost exactly the 1 in 3 we counted with the dots. Sit with why. The test is strong. But the disease is so rare that the few real cases are outnumbered by false alarms from the huge healthy crowd. Bayes weighs accuracy against the prior, and the prior wins. Bayes isn't limited to two causes. A factory has 3 machines. Machine 1 makes 30% of output, 1% defective. Machine 2 makes half, 4% defective. Machine 3, 20%, 2% defective. You pull a defective item off the line. The question flips the arrow again. Which machine most likely made it? Let's find the chance it was machine 2. Same recipe, Bayes on top. But the denominator now sums over all 3 machines. Build the denominator first. Defect rate times share for each machine. 0.003 plus 0.02 plus 0.004. They add to 0.027. Now the top, machine 2's contribution, 0.02, over the total, 0.027, and the answer is about 74%. Machine 2 makes both the largest share and the most defects, so it's the odds-on culprit. One last check, always worth doing. Run the same division for the other 2 machines. The 3 posteriors account for every defective item, so they must add to 1. And they do, exactly. Your turn, and this one you can fully solve. A spam filter watches for the word urgent. 1 in 5 emails is spam. The word urgent shows up in 60% of spam, but only 10% of real mail. An email arrives containing urgent. What's the chance it's actually spam? Pause here and work it through with Bayes before I do. Here's the walkthrough. First, the denominator. The overall chance an email contains urgent by total probability. That's 0.12 from the spam plus 0.08 from the rest. Together, 0.2. Now Bayes, the numerator is the spam path, 0.12 over the total 0.2. That divides cleanly to 0.6, 60%. If you got that, you've genuinely got Bayes. And notice, urgent appears in 60% of spam, and given urgent, it's 60% spam. They match here only by coincidence of the numbers. In general, those two are different. Trap 1. The deadliest, reading the likelihood as the posterior. The chance of a positive test given disease is not the chance of disease given a positive test. Flipping the given flips the answer. Trap 2. Ignoring the prior. Stare only at the test's accuracy, forget how rare the disease is, and you'll wildly overestimate. A tiny prior can drown a strong likelihood. Trap 3. an incomplete denominator. P of E must sum over every way the evidence can arise. Miss a path and the whole ratio is wrong. And trap 4. Sloppy complements. The healthy fraction is 1 minus the sick fraction. Keep every probability between 0 and 1 and check your posterior sum to 1. Let's lock it in. Bayes flips are conditional. The cause given the effect equals the effect given the cause times the prior over the evidence. That evidence comes from total probability. Sum the likelihood times the prior across every possible cause. And in plain words, posterior equals likelihood times prior over evidence. Name your events. Honor the prior. Sum the denominator over every cause. And Bayes will flip any conditional you meet.